Hi there, I am Veronique Florec from the University of Western Australia. Welcome to this course on the economics of natural hazards. I have created this video series for anyone in the natural hazards and emergency management sectors that is interested in learning how we apply economic analysis to the management of natural hazards. This project is funded by the Bushfire and Natural Hazards Cooperative Research Centre. Welcome to the video number 7 in the series. In this video, we'll have a look at how we calculate the benefits of mitigation options. After watching this video, you will understand why it is so important to be clear about the counterfactual. You will know what the benefits corresponds to, and through an example, you will learn to estimate the potential benefits of mitigation options. I'll continue using the flood example from previous videos, but keep in mind that all the principles that I am presenting here can be applied to all natural hazards. So instead of flood damage and losses, we will have bushfire damage or cyclone damage or other. The mitigation options will be different for each hazard, but the way we estimate average annual damage and the cost and benefits of each option is the same. So in our flood example we had the average recurrence intervals for different flood sizes, the annual exceedance probability, and the amount of losses for each flood size if there is no mitigation. That means that in this example, our counterfactual, or the base case scenario, is a no mitigation scenario, or in other words, a do-nothing scenario. Two options are being evaluated for the catchment. Option A is the construction of a dam in the upper section of the creek, and option B involves upgrading the capacity of the creek. The aim of both options is to provide protection to the catchment for up to a 1 in 100 years flood. Here is how each option will contribute to the reduction in flood damage for floods of different sizes. Option A, the dam, will reduce to zero the losses caused by floods of an average recurrence interval of 2, 5, 10, 20 and 50 years. It will also reduce losses caused by a 1 in 100 year flood to $350,000 and have a small effect on losses caused by larger floods. Option B, upgrading the creek capacity, will also reduce to zero flood losses of up to a 1 in 50 years flood. It will reduce losses from a 1 in 100 years flood to 13.5 million and have a smaller effect than option A on larger floods. Now, let's calculate the average annual damage for option A and option B. I'll use a trapezoidal sums method so that we can revise the method. We already have the result for the base case scenario, which is 2,029,000. Now, let's do the same for the two mitigation options. The only thing that has changed between the best case, which is a do-nothing scenario, and the implementation of the mitigation options is the level of damage. So we can use the differences between the annual exceedance probabilities that we calculated before, and I'll put them again in this table. Here we had done 0.5 minus 0.2 equal 0.3, 0.2 minus 0.1 equals 0.1, and so on. Now we do the sum of losses for pairs of floods of different sizes for option A. 0 plus 0 equals 0. Here is the result, so 0, 0, 0. 0 plus 350,000 equals 350,000. 350,000 plus 46 million equals 46,350,000, and so on. For option B, it's the same. 0, 0, 0, and 0. Then 0 plus 13,500,000 equals 13.5 million. 13.5 million plus 57.3 million equals 70.8 million, and so on. Then we multiply the sum of losses for pairs of floods of different sizes by the difference in the probabilities for the same pair of floods. We do the sum of all that and divide it by half. And we get an approximate estimation of average annual damage using trapezoidal sums. Average annual damage for option A is $1,120,150, and for option B is $1,291,100. Now that we know the average annual damage for all scenarios, the base case, the implementation of option A, and the implementation of option B, we can proceed to the estimation of benefits from the mitigation options. The benefits are simply the difference between losses for the base case scenario and the losses of the option that we're looking at. In other words, benefits correspond to the reduction in damage achieved by a mitigation option compared to the counterfactual. This is why it is so important to be very clear about what a counterfactual is and have a very clear definition of the scenario for the base case scenario to be able to estimate the benefits, because the level of benefits will always depend on what we have selected for the counterfactual. So the benefits of option A are $2.029 million minus $1,120,950, which is equal to $908,050. And the average annual benefits of option B are $2,029,000 minus $1,291,100 equals $737,900. So the benefits of option A are higher than the benefits of option B. So far, if we leave it at that, option A looks more attractive than option B. But the problem here is that we don't know yet how much it cost to implement option A or option B. So we have not compared the benefits with the cost yet, and that is very important in order to guide decisions about mitigation for natural hazards. So we'll look at that in the next video. Also, we haven't had a look at timeframes for the analysis. Are we doing an analysis for 10, 20, 30 years or more? And why do we do this counting? We will look at that in the next video so that we go step by step and get a good understanding of all the principles that apply to economic analysis of mitigation for natural hazards. In summary, now you know why it is so important to be very clear about the counterfactual, because it is the base scenario against which we compare the outcomes of mitigation activities. The benefits correspond to the difference in losses when mitigation has been implemented versus the counterfactual. So the level of benefits will change if we change the counterfactual. Okay, thanks for watching. I hope you enjoyed this video. In the next video, we will look at how to include the cost of mitigations in the analysis to compare them with the benefits. And I will also talk about timeframes for the analysis and how and why we use discounting.